Danikers, welcome back. This is John Hansen, and I'm here to talk about this dihydronaphthalene spectrum as a way to sort of show you how to analyze maybe slightly more complex splitting patterns than the normal doublets and triplets and quartets that you're used to. And also as a quick review of how to just analyze a spectrum in general. So if we see the structure of dihydronaphthalene up here, let's just kind of look at the different protons. We're talking about the proton NMR now. Unfortunately, I haven't shown the protons on the ring, but you can see at these 4 positions there would be protons at those positions. At these junctures right here, they already have 4 bonds, so there's no protons there. So there would be 4 aromatic protons. Where do the aromatic protons come? Do you remember? Well, if you remember from our little cheat sheet, we usually say they come from about 6.5 up to about 8.5. And if there's no electron withdrawing or electron donating groups, just alkyl groups on it, they're typically right around 7 to 7.5. And so you see right here, this integral is going to integrate to 4 protons relative to this one right here. And so there's our 4 aromatic protons right where we expect them. It's quite a complex mixture because those 4 protons have very similar chemical shifts, so it's pretty hard to analyze. Maybe we could analyze this one right here as a doublet, which means it must be one of these hydrogens on the edges here. If it was one of these hydrogens, there'd be a hydrogen neighbor on either side, so it would look more like a triplet. But it was complex enough that I decided I wasn't going to worry about it, and I was just going to call it a multiplet. And so you can see over in the line listing right here, I just list the range of those peaks from 6.95 to 7.2 here, and I call it an M for multiplet, and it integrates to 4H. So that's how I would write up that group of protons. All right, so having sort of taken care of the discussion of those, I now move on to all of these protons that are on this other attached 6-membered ring. And you can see there's sort of 2 different classes. There's HA and HB, which are attached to an alkene type moiety right here. And then I've got HC and HD, which are, in our way of talking about chemical shiftings, we might say that they're on a carbon that's next to an sp2 carbon right here. So if we think of HA and HB first, and we say, oh, they're on an alkene, what's the alkene range? Do you remember? Right, it's around 4.5 to 6.5 ppm is where those normally come. Now, it's interesting, you can see that these are sort of up at the upper end of that. This one's almost nearly at 6.5. And that has to do with this HA being right next to the side of this aromatic ring. Remember, aromatic protons come shifted quite far up in the NMR because of the ring current effect, which causes these protons to feel a magnetic field that causes them to come up to higher chemical shifts. And HA is sort of on the same sort of location. I mean, it's not exactly as close as those guys, but it also gets to feel some of that ring current effect, so it gets shifted up further than HB, which is out here. And so it's up near the top of our range. You might say, well, what about HC? Is that similar to comparing it to HD? Because HC is kind of near the edge of that ring, and sure enough, here's our HC protons coming at slightly higher chemical shift than the HD protons. So we see the same thing occurring in that situation also. So let's start first with HC because it's fairly simple analysis. If we look at HC, these 2 HCs, I've labeled them the same because they're equivalent for NMR purposes. Now, how do we really know they're equivalent? Well, one way to do it, and probably the best way to do it, is to replace the H with something else, like, I don't know, a methyl group, for example. And then replace the other H with a methyl group, and then compare those 2 compounds. And what you would find in this particular case is if you put a methyl at one of these places and left out an H, you'd actually have created a chiral center. And what you would have done is you would have actually made 2 different enantiomers by doing that. So we would call those 2 hydrogens then enantiotopic. And enantiotopic protons are equivalent for NMR. So those 2 guys are equivalent. HD and HD are equivalent to each other also. But of course HD is not equivalent to HC because HC is next to the aromatic ring and HD is next to this alkene part. So if we want to look at HC and think about its splitting pattern, which is what the main point of this little video is, is we want to count the number of neighbors. Now remember, we don't count this HC as a neighbor because they're equivalent, so they don't split each other. But if we look at the HCs and we say, okay, there's 1 bond, 2 bond, 3 bonds away is another proton. So those 3 bond neighbors are going to give rise to splitting. If you say, well, what about on the other side? And we say, well, there's 1, 2, oh, but there's no hydrogen on that position. So to get over to hydrogen over here would be 1, 2, 3, 4 bonds away. So initially we're not going to worry about that. So we're going to say, okay, 3 bonds away, there are 2 neighbors for HC. So what kind of a pattern do you get for a proton which has 2 equivalent neighbors? Remember the n+1 rule? 2 plus 1 is 3, so that's a triplet. So when we look at HC here, it's a triplet, and I've shown a blown up version right here. So this is just this region blown up, and you can see there's 1 to 2 to 1 ratio of these 3 peaks. You'll also see that I've labeled these with their chemical shift now in hertz rather than ppm. So although this comes at about 2.8 ppm, it comes at 842 hertz. And if we want to actually know what the coupling constant is for a triplet, we just subtract the 2 lines, the first line and the second line. And you might not be able to quite see this. This is 42 and that's about 34. So when we subtract them, we get about an 8 hertz coupling constant. So in my line listing here at 2.78 ppm, which is where the middle of this pattern is, I say I have a triplet with a coupling constant J equals 8.0 hertz, and it integrates to 2H. So that's pretty easy to take care of that sort of analysis. If I look at its neighbor HD, you can see here's the blow-up of that. It's quite complex. I ended up calling that a multiplet. 2H, that's what the integral was, and I gave the range over which those came. Now maybe by the end of this video you might actually be able to go in and analyze and draw a splitting tree for what that really looks like, but that's a pretty complex pattern, so I was a little bit lazy and didn't bother to do that. Okay, now let's come back to HA and HB, which are kind of a little more complicated than normal sort of splitting patterns like the triplet, but are still pretty analyzable. If we just look at HA, which is right here, and again, here's HA that I showed originally, and now I've blown it up so we can see it, you can really see that this looks like a triplet, and then there's another triplet. So we might see, oh, that's like a doublet of triplets. And let's just see what we think if we look at HA. So if we look at HA and we say, okay, how many neighbors does it have? Remember, it doesn't have a neighbor over here because there's no hydrogen. So we just go over here and we say, oh, there's HB, 3 bonds away. So it's got 1 neighbor. And if we just stop there, we say, okay, it should be a doublet. And in fact, if you look at this blow up, it looks like it sort of is a doublet. But when you zoom in, you say, wow, it's not really a doublet, it's like a double triplet. Why is it a double triplet? And the reason for that has to do with this unusual 4-bond coupling that we're seeing. So this HA, if we count, there's 1, 2, 3, 4 bonds over to HD. Now, in most cases, we don't see 4 bonds coupling, but there's one case where we often do, and I was just going to refer you to our little coupling sheet that we had. If we looked at 3-bond coupling, so here's like a normal 3-bond coupling, it's 6 to 8 hertz, and that's what we found for this proton right here, HC. Remember, that was about 8 hertz, so that was kind of normal. If we think about on a double bond like this, which is sort of what we have in our system, it's 6 to 12 hertz, and typically it's usually sort of toward the upper end of that range, but that's fine. But then notice down here is a 4-bond coupling. So here's HA coupled to another proton HB by 4 bonds, and you can see my little note here. 4-bond couplings are usually not observed if there is not a multiple bond between the 2 hydrogens. Another way of saying that, I guess, is that if there is a multiple bond, like a double bond between them, there is more commonly seen a small coupling constant. Now you can see it's 0 to 3 hertz, so if it's less than 1 hertz, you're probably not going to see it. But it can come up, and so you shouldn't be too surprised if you see it. So if we go back to our system here, and we think of HA, there's one there, it's going through a multiple bond and then a single bond, and there's a HD, so that certainly fits into that category. And there is a little bit of splitting there. And because there are 2 of them, it splits that into a triplet. If we wanted to know what the coupling constant was for that, we would just again subtract the numbers between these two lines. And if you see this one, let's round that off to 41 and round that off to 39. Well, 41 minus 39, that's 2 hertz. So there's our 2 hertz coupling that's right in line with what we had on our little sheet here, 0 to 3 hertz. So just pretty typical for a long-range coupling. So we see that, and we see each of those being turned into a triplet. Now, when we're analyzing complex spectra like this, with multiple couplings of various magnitudes, it can get a little tricky. And so what we're going to do here is I'm going to show you how to do a splitting tree, and you're going to be doing this for your homework assignment also. So I thought we should go through it together and look at it. Now, when I looked at HA and analyzed it fully, let's see here, you can see that I called it a double triplet, and it had a J of 9.6 and 1.9. So this was the coupling constant from HA to HB was 9.6 hertz, which is right in the range we'd expect for a cis double bond. And then we'd have our 1.9 hertz for our long range. For simplicity, when I do the splitting pattern, I'm just going to round this off to 10, and I'll round that off to 2, and we'll draw that splitting pattern. So to do that, I'm going to go over to my ChemDraw drawing area, and I'm going to use this to draw my splitting pattern. So we're going to draw the splitting pattern for HA, and so I'm going to start with a single line. I'm just going to start right here in the middle, and I'm just going to draw up a big black line. There it is, and that represents my HA before it's been split. So maybe I should label that just so it's clear. So this is going to be H subscript A. There it is, okay? Ready to go. That's if it didn't have any neighbors, it would just be sitting at some position like that as a big single. Well, let's go through now and do the splitting. So we know it's split by HB, and we said that that's about a 10 hertz coupling constant. And we know that from having looked at the spectrum, but even if we had never seen this spectrum, we could use our chart and say, oh yeah, it's in that 6 to 12 range, so maybe picking something like 10 is not unreasonable. So what I need to do now is I need to split HA because of HB. So maybe I'll write a little note to myself, HB splitting here. Okay, and what I'm going to do is I'm going to split it into 2 peaks. Now, if the coupling constant is 10 hertz, that means the 2 peaks that I have will be 10 hertz apart, which means I need to go 5 hertz one way here and 5 hertz the other way. Now on my sort of graph paper that I have here, I've decided that each of these little blocks is going to be worth 2 hertz, and so I'll know how far to go over. So if I want to go over, I'm going to go over from this position 5 hertz. So there's 2, 4, 5, and now I'm going to draw my peak right there. So that's showing that this peak right here has been split to that peak. Now, the other thing notice I'm doing here is I've started off with this being 4 units high, and now I have it 2 units high because when I split it, half of the intensity goes this way, and the other half goes the other direction. So let me draw that one. So again, I'm going to start here. I'm going to go over another 5 right to there, and I'm going to draw my peak. Same height, there it is. Okay, and if I want to sort of connect it with a dashed line so I can see those two go together, there it is. I might also indicate that these 2 peaks are 10 hertz apart, so I could just type in here 10 hertz to remind myself, and I could draw a little arrow from one to the other. There, and then that guy's going to there. So there's my 10 hertz coupling constant for HB. Okay, so I've taken care of that one, but now I have to do the HDs. Now because there's 2 of them, I'm going to have to do it twice. They both are equivalent, so they're going to have the same coupling constant. And remember we decided we were going to use a 10 hertz coupling, a 2 hertz coupling constant so I'll label this one maybe here HC splitting. Oh, sorry, HD splitting. So there it is, and now I'm going to split those by 2 hertz. Now, remember, that means I'm going to go over 1 hertz one direction and over the other direction 1 hertz. So again, I'm going to decrease the intensity by half. So I'm going to start down here, and I'll go up 1. So I started from that position. I went over 1 hertz. Remember that one box is 2 hertz here. And then I'll come over the other direction here, the same position, make that go up. There's another 2 hertz, and so those two guys are connected this way. And I need to do the same thing over on this signal. So, little guy. So I'm going to come. Here's where I start in the middle. I go over 1 hertz right there. Make that guy half height. And I'm going to come over here and do this one. Same thing. There we go. And now that's if I only had 1 HD, I'd have this pattern. Can you tell what that would look like? That would be a double doublet. Okay. And maybe I'll just remind me. Oh, maybe I can just grab this guy over here. Let's see if this works. And I'll just copy that, and I'll try to paste it somewhere. Grab it, move it down here, about right. It's kind of hard to see there, but there's our 2 hertz coupling right in there. Okay, this would be a double doublet giving rise to 4 lines. But remember, there's 2 HDs, so we have to do another one. So maybe I should copy and make another copy of that and say, okay, let's do HD splitting again. So this time, same difference. But now what you're going to see is something a little interesting happen. So I'm going to start at each line. So let's start at this end line here. I'm going to go over 1 hertz. Let's see, I'm going to start down a little bit lower here, just so it doesn't run into the other one. And I'm going to go up now half the height of one of those squares, because this is now 1 square high. Now I'm going to come over 1 hertz on this side and go up half a square. That's good. And there's my splitting of that peak. Now I have to do this peak. So if I go over to the left 1 hertz, come up half of a square. Okay. But now I also have to go this way, and remember now look, that's right on top of that peak. So I have to add on to that another half square and bring it up to a full square. And now you can see our triplet pattern. 1 to 2 to 1, our triplet, and we can sort of show where it came from. By doing that. Now, we need to do the same thing with these 2 lines over here. Let's see if I can do something tricky here. I probably won't be able to. But what if I just circle these and copy them and then paste them and move them over? They should look exactly the same. Oh, yeah, that was pretty slick, huh? And now I can draw my lines connecting. So that went over that way, that went over that way, that way. And that went that way. So there's my splitting, and now you can see I have a triplet and a triplet, so that's a double triplet. You can also tell that the distance between lines 1 and 2 and lines 2 and 3 is 2 hertz. So the distance, it turns out, in any coupling splitting pattern you make, the distance between the first line and the second line in the pattern will always be a coupling constant. But notice the distance between line 1 and line 3 in this pattern is 4 hertz. That's not a coupling constant. That's just sort of the sum of 2 coupling, of the 2 hertz couplings. So if we wanted to measure the 10 hertz coupling, you can see what we'd really want to do is measure the top of this triplet and the top of that triplet. Or we could measure the first line in this triplet and the first line in that triplet. Should give us the same 10 hertz value. So let's see what this looks like, this double triplet, and compare it to the real spectrum. There it was, so there's our double triplet, so you can see what that looks like. And there's what it looks like under those conditions. Now you might say, well, what if I did them in the reverse order? What if I did, instead of the HB splitting, what if I did the HD splittings first and then did the HB splitting? Would that work? And the answer is absolutely. It would give you exactly the same answer. It might be a little complicated because there'd be some lines crossing over. Maybe we should try that. Should we try that real quick? Let's just see if we can do that. So I'm going to try to move this over. Okay, let's move that guy over there. Here. So what I should do is select this whole area. Move it over. Good. Let's get that out of the way. Move that kind of over there. All right. So let's do it in the other order. And I'm going to try to do this a little faster because I know you're getting a little bored here. And to do that, let's say we do the triplet first, and we know it's a 2 hertz triplet, and so we can just sort of start out and say, okay, well, if it's a 2 hertz triplet, oops, let me use my little wider line here. Let's start here, and I'll make it this high now because I've already going to have it split, and it's going to be 2 Hertz over here is going to be half the intensity, and then over here is going to be half the intensity. Okay, so there's my triplet with a 2 Hertz coupling constant. Essentially, it's this part right down here that I've done already. So I've saved myself some time by not drawing a little splitting tree for that. Okay, so now we're going to split each of those lines into 2 by using, so we've done sort of this coupling already. Now we're going to do the splitting to HB, which is the 10 Hertz one. So let's see how that works out. So let's start with this right-hand line, and I need to do 10 Hertz, so I have to go over 5 Hertz. So if I go over 5 Hertz, that's 2, 4, 5, and then I'm going to come down, so I'm kind of not right on top of it here. And let's do that. So now I'm going to do half the intensity, so there it is. And now I've got to go over 5 this way, so there's 4, 5, and come down to the same point. Let's see here. Okay, that looks good. Okay. Now, notice that that line is going to that one, not to that one, so don't get confused. Okay, so now we're going to move over from this line and split it. So 5 Hertz is over to there, come down, and that's going to be twice as intense as the other one, so it's going to be, let's see, a little bit off. How about right about there? Okay, and now go over from this position 5 Hertz the other way. 4, 5, okay, come down here. You can see why graph paper is useful here. Okay, and now I've got to do this line. So now if I go to the right, go over 5 and down, there, it's going to be right there. It's going to be half the intensity. And then go over 5 there and down this way. And there it is. So look, there's my double triplet. If you wanted me to sort of show the connectivity, it gets a little bit complicated here because those two go to those two. That one goes to that one. And then this one goes to this one. So you can see that there's a little bit of sort of crossover here. But it gives you in the end the exact same pattern. I usually like to do the large ones first and then the small ones just because there's less of this sort of thing. But just to convince you that these are exactly the same pattern, let's see if I can do this. What if I just grab this pattern and just try to move it? And there it is, right on top of that pattern, exactly the same. So you can see that you can easily produce the same pattern either way you want to do it. And in fact, one way to sort of think about triplet patterns is, you know, you could take one triplet and you can just start moving it relative to the other, and you can have all sorts of things. So you could have things that sort of look like this, where that middle peak would be like twice as high. Or you could have something like this. What if the doublet was the small coupling constant? You'd have something like that. So if we changed around and instead of having the doublet be 10 Hertz, what if the doublet was 2 Hertz and the triplet part was 10 Hertz? You'd have something that looked like that. So you can have all sorts of different patterns. Notice that in all of these double triplets we have 6 lines unless there happens to be some overlap. Oh, what's that one? Well, if these guys overlap, that would actually be a quartet. And that would be a case where all 3 of those coupling constants, the 2, so we have a 10 and 2 2s right now. If they were all the same, then you'd have a quartet, which is what you knew anyway. But then we could have, again, you know, all 6 lines. They could be interdigitated. And if we have just those guys kind of overlapping, notice there we would have sort of 5 lines. It's hard to see that this line right here could be a little bit bigger. But in fact, we do see that in our pattern. Notice our HB is going to be a double triplet, because this coupling constant between HB and HA is not the same as the coupling constant to HD. So in fact, notice here we've got 1, 2, 3, 4, 5. Where's that 6th line? It's right on top of this one. Now, it's not such on top that it's exactly the same height as these because it's a little broader. You can see if you look at how sharp that peak is and how sharp that one is, that one's just a little bit broader. So if you integrate it, it would actually integrate to twice as much. So you see a pattern that looks like this. So what I'd like you to do is go draw your own splitting pattern and see if you can't reproduce this. And I've already done a lot of the work for you by pulling out the coupling constant. So let's find this guy. This is right at 6 Hertz. So there it's got a coupling constant of 9.6 hertz. Remember, that's the coupling constant from HB to HA. And then the coupling constant to HD is 4.5 hertz. So that's this one. So again, you could try it out and maybe round them off to 10 and 5 or something to do your splitting patterns. And you should come out with something that looks just like that. If the two lines in the middle, when you draw your splitting patterns, are within a hertz of each other, usually you don't see them as separate peaks. You just see it as lumped together. And so that's kind of what's happening in this particular case. Well, I'm going to let you do that on your own, and hopefully you can reproduce that. But I wanted to finish off by just asking you this curious question. Remember I said I was a little lazy on this, and I just called it a multiplet. Well, what should it actually be? What is it actually? So which proton is that? Or I guess which protons? That's HD. So what would its pattern look like? Well, before we were thinking of long-range coupling, we might have thought, well, there's an HB there, so that'll split it. And then there's two HCs, so it could be a double triplet. Now, if the coupling constant HB happened to be the same as HC, then it would actually look like a quartet, but we could probably guess that they might not be exactly the same, so we'd say, okay, a double triplet of some sort, okay? But then when we see it's more complicated, we say, oh, there must be something else going on. Oh, it's that long-range coupling, and we already knew that because we did HA first, and we saw there was a long-range coupling from A to D, so that means there must be a mutual coupling back the other way between D and A. So we know that there's that, and we actually know what the magnitude of it is. It's exactly what we found in HA of 1.9 hertz. So if we wanted to actually draw this pattern, that is, go ahead and try to do like we did that splitting tree, what we'd have to do is we'd have to get this coupling constant, which we know is about 4.5 hertz. We'd have to take this coupling constant, which we know is about 8 hertz, and we'd have to take that coupling constant, which we know is about 2 hertz, and apply them all. So now we would have a double-double triplet. And how many lines in a double-double triplet? Well, 3 for the triplet, times 2 is 6, times 2 is 12. So that's a lot of lines, and there they are. But you could actually stretch it out, and you should probably get something that looks just about like that. And if I had expanded this even more, you might have been able to see all of those individual peaks. But it's a little too fuzzy here to tell exactly what's going on. Well, that gives you a little bit of instruction on how to do splitting trees for your homework assignment. You'll be doing the similar sorts of things, and being able to analyze all of these coupling patterns is very powerful when you have complex molecules and you're trying to see which protons are coupled to which and how the molecule is connected, because once you start figuring out those splitting patterns, it allows you to figure out how everything is connected to each other. Very good. That's all for now, and we'll see you in class on Monday.